Hello, and welcome to the next lecture of a parallel programming. So, in this system designed for the parallel programming, so we need to first describe what are the parallel systems which are comes in, and there are many flavors. So, according to the Michael Flynn, so he described it as Flynn's taxonomy as this one. So, first one is a SISD, as you can see. So SISD is nothing but a single instruction. So you have only one instruction to execute and single data. So you have one instruction, one data source. And this is nothing but an example of a traditional single core CPU. So you can only run one instruction at a time, execute one data access at a time. Okay. So that's SIS. Then comes the next category where it stands for single instruction, but multiple data. So we only have one instruction, but we have a same operation, same instruction to be performed across the multiple data inputs. For example, vector processing or matrix operations. So if you recall, if you need to add two matrices, so you have a n cross n matrix or you have m cross n matrix. So you have a same instruction set to perform the arithmetic addition, but across the various data. So you have multiple data, but only single instruction. Only operation to do is addition. So that's a single instruction, multiple data set, which are used in the GPUs, for example. However, now when we go next, MISD, which is nothing but there are multiple instruction. You have multiple instruction, but you have only single data source. And this is a extremely rare scenario, and it's kind of used into the fault tolerant systems. So this is not something that we would be going forward and discussing into the syllabus. Now comes the next. It is a multiple instruction, multiple data. So as you can see, it's like a mix. It's one of the most commonly used and deployed ecosystem where you have multiple core CPUs or GPUs and you have distributed across the systems. So eventually you can have just multiple cores or multiple GPUs with one single setups, or you have the same kind of setup and you are distributed across your clusters. So this is what Flink's taxonomy. So this is very essential to know in terms of a parallel programming, because this is how your data is going to be distributed and it cannot be accessed. So what exactly are the techniques which are actually used in parallel programming? So let's see. So there is a two-way you can actually decide how you will distribute your parallel programs. Okay, so first thing we have is a data parallelism. Okay, so what does data parallelism defines? As we need to divide a very, very large data set into smaller chunks that are processed in parallel. So basically, you can perform the individual operation in the parallel. Take an example. If you have a vector where you have elements 1, 2, 3, and so on, and you have another vector matrix, and your elements say 1, 2, 3, and 0. Let's repeat it for example. Now, if you are doing the addition of this two, so you know how it happens. 1 plus 1, 1, 2 plus 2 is 4, 3 plus 3 is 6. So this was the addition. Even if you have a multiple operation. So instead of addition, if you are doing a multiply, so I would rather add it as a dot product. So if you are doing a dot product, then just need to do is multiply 1 to 1, 2 to 2, 3 to 3. And if you do the multiply, your result would be 1, 4, 9, and so on. So what happened here? So you may have a very, very large data set. And this is just an example that it's one of the simplest arithmetic operations. So you have divided your data into smaller chunks that you can divide. You can tell that, okay, first three numbers is processed by the core 1. Next three numbers is processed by the core 2, and so on. This is a classic example of a data parallelism where you don't need to rely on the calculations of any previous steps. The addition of these three is independent of any further numbers which are coming. Even not just these three, every instruction is individual on its own, whether I do dot product or addition. So it's independent, which is why we can divide into the smaller chunks of like 5, 10, 500, whichever it is, based on the system configuration. That's what we are going to learn as part of the system design. But this is what we need to take in account, that this is the data parallelism. So what is another type of parallelism? So another type of a parallelism is a task parallelism. Yeah, you would have guessed it right. In the task parallelism, we would be distributing independent tasks or functions across the multiple computing unit. So what would happen? So let's say you have multiple tasks to perform. Instruction 1, instruction 2, instruction 3. And what you will do is every instruction you are distributing across the system. Let's say this you have assigned to core 1, this you are doing to core 2, this you are going to core 3, and this may be the same machine, or you can say it's like a different machine. So you see, there is a system. Let's say it has a SSH connection with some IP address. This is another system with another IP address. Say system 1, this is system 2, and you are doing this over system 3. So this is what the classic example of task parallelism, where you may have a web server handling several user requests at the same time, where each request is processed by a different thread or a different machine on its own. So you may have a website design. The user is continuously coming and asking from a different geolocation or a different regions, and what the server needs to do. Based on the whichever is the short spot, there can be different server which is picked up and the task has been executed and the user is getting the response. So this is a classic example of a task parallelism. These models are the foundational in achieving the speed up and efficiency, but they also necessitate careful design to avoid pitfalls like race conditions and the deadlocks. We'll further study more about the parallel computing next series of how we design the system design. So this is a very important concept that we understand at how we are working with the data parallelism, how we are working with the task parallelism. And this is the core important factors. So when you are working with the GPUs and you are writing your GPU program, that is nothing but a data parallelism. And why it is faster with the data parallelism is because the way it is designed. So, so going forward in the next session, we will learn more about the building blocks of the parallel programming with the how we can differentiate based on the hardware.